a lot. Great. Welcome, everyone. Good morning, good afternoon, good evening. Hope you enjoyed this today. I really enjoyed preparing the material because it's a really fun aspect of looking at the different databases and the different data models and see how they relate to each other and how you can transform one into the other. To get started, first a disclaimer. I hope most of you already know Neo4j because I will not do the intro part. I will only talk about modeling aspects today, not the actual import, which is a topic of the next webinar. And content of this presentation, some of the content is taken actually from our data modeling training. So if you want to have the full-fledged content of all this, feel free to attend one of the local training classes. And I also will not do any customer use case related things here today. Agenda, I want to look at the different models, at the graph model, at the relational data model. I want to compare them, of course, and then discuss how we can get from the relational model to the graph model with different ways. And then at the end, we have some questions. And as Greta said, you can also tweet your questions to @Neo4j as well. Okay, let's quickly get over the labeled property graph model. Most of you already know this. Just to recap, so in general, we have 4 building blocks in a graph. So we have nodes with labels and properties and relationships which form directed connections between 2 nodes and which have a type and can also contain properties. So if we dive a little bit into detail, it looks like this. So nodes in a graph are your entities of your domain. So everything that you talk about when you talk about your domain is an entity. It usually has an identity and has a number of attributes. Different entities in your domain might have really different attributes. Even entities that are of the same type, depending on how much information you have about each of these entities, might have different amounts of attributes or properties. So nodes are instances. Nodes are not like in tables categories or classes of things, but nodes are really the instances. So what you would draw is a circle on a whiteboard. Your nodes in a graph might have labels. Most of the nodes nowadays have labels. I'll talk about that in a minute. And nodes can also contain properties, which either represent attributes or metadata about your entities, like when was it created, which version it has, by whom it was created, and so on. In general, if you know domain-driven design, which is really recommended, a recommended read, a book by Eric Evans, then entities relate to the entities that you have in domain-driven design. So that means these are objects in your domain that have an identity, and their attributes change over time, but their identity stays the same, and they have like a life cycle from being created or being added to the domain until they are retired. On the other hand, nodes can also be value types, which are more complex attributes. Those don't have an entity, but they have still a complex structure. For instance, an address or a color or something like that could be a value type. So, and they are substitutable, so you can exchange one value type for another. These value types are oftentimes used in things like recommendation setups where you want to relate entities across certain values or attributes. As I mentioned, we can have labels in our graph for nodes. Those are case-sensitive names and are representing roles of your node. So a single node can have multiple labels, 0 or more, and these labels represent roles that your nodes have. So even if you have the same type of node, for instance, a person, this person can have other roles, like this person can be a developer or a manager or a husband and father and employee, everything at the same time. But each of these labels has a different set of attributes and relationships that it relates to, and that you would look at when you deal with this node with this label in this context. And so you can also say labels form sets of nodes. So a label might be like a projection of a table in a relational database or a view. And the nice thing about labels is also that they allow us to attach meta information to nodes or to groups of nodes, for instance, indexes and constraints. And in the future, we want to add much more optional meta information to those labels as well. Between our nodes, we have relationships. That's where the whole graph concept comes from, right? So in the graph model, the relationships are really first-class citizens, not something that's computed at query time, but something that's really stored as data structure in database and really managed and handled efficiently as part of your data. Relationships in the graph have a name, as you can see here in the small picture, and a direction, but you can choose to ignore the direction if it's not relevant for your question or your query. If you only have nodes without relationships, then they're just pieces of information that exist in isolation. But with relationships, you actually get a semantic structure. So you can put nodes into context, you can relate them to each other, and you can infer much more information about each of your nodes by following its relationships. Either just one step out or also multiple steps out. And then you see your entity in a bigger context and you suddenly know much more about it. Like nodes, relationships can also contain properties. And for relationships, oftentimes these properties represent qualitative information like weights, distances, time information, ratings, and so on. And of course, metadata is also possible. But you're not limited in what you want to put on a relationship. There's actually only one consistency rule in this graph model, in this basic graph model, which is there are no dangling relationships. So there are no broken links like in the web, but each relationship is guaranteed to have always a start node and an end node. So that's kind of the consistency constraint in a graph database. There are some more things around relationships. So a node can have as many relationships as you need. So it can be everything from 0 to 1 million or 10 million. And nodes can also have different types of relationships in different directions, depending on what the semantic meaning is that you want to convey. Also, between the same two nodes, you can have multiple different relationships, which then might be qualified by their name or by additional attributes as well. And we also allow self-relationships, which sometimes come in handy. As I mentioned before, relationships are connecting nodes. So that means they connect instances. So they would connect a person to another person. So they would, for instance, connect Michael to Greta, and it would be a knows or works with relationship. And in contrasting them with relational databases, where this connection information is implicitly stored in foreign keys, which are the same as a primary key on another table, where you actually have to find the mapping between the foreign key and the primary key at query time. In a graph, it's really that the relationships are more like a pointer that points from a node to another node, and each node has the list of all its pointers stored with the node as well. So that allows us to really provide a really fast way of following these relationships. And so we don't need to have a value that says here is no relationship, so where a foreign key would be null in a relational database. Properties on nodes and relationships are attributes, and they have a case-sensitive name. And they can be strings, numbers, or Boolean values, or arrays thereof. And null is not a valid value. So you would just leave off properties that are null, because Neo4j is a schema-free database, so there's no need to put in null values for columns or default values if you don't need them. So you can always derive default values also, for instance, at query time. You don't have to fill your database with meaningless default values, for instance. And every node, even with the same labels, can have different properties. Oftentimes, nodes with the same label share a basic set of properties. Like, for instance, nodes with a person label might all have a name and a birth date and a something else property as well. Okay, that was quickly about the graph model, which I hope you all are already familiar with. And now let's look at the relational data model. First of all, the fun fact that the relational in the relational data model is not about relationships, but it's about mathematical relations, which are actually represented by tables. So when someone talks about relational data or relational databases, it's really not about connections between tables, but it's about the tables themselves. So the tables form these mathematical relations which group rows, meaning tuples, into a set. And that is sometimes cause for some confusion. In general, the building block of the relational data model is a table. Each table has a name. It could also have like a schema and a catalog as well. And in the table, we have attributes, which are columns, which also have a name and a type, and rows with data for each of these columns. And then tables usually have primary keys for lookups and also identities. We sometimes also have multiple keys to find data in tables, which might be then business-based keys, and then primary keys are oftentimes also technical keys, like just auto-increment values. The number of types that the database supports is really different. So some databases only support simple types in the relational model, but other databases, like for instance Postgres, have a gigantic number of types that they support, including JSON and also custom types as well. So you can go from very simple to very complex in terms of types of your columns. If you look at relationships, relationships this time in a relational database, those are really just represented by foreign keys. So that means in my table, I have a field which says, this is a foreign key to this other table, and we can represent different cardinalities of relationships there. So a one-to-one relationship would be just a foreign key to one other table plus a foreign key constraint. A one-to-n relationship would be a reverse foreign key, so the other table would contain our own primary key as foreign key and also contain the constraint for that. And as soon as we get into higher cardinalities, many-to-many relationships, we have to introduce a new table, because that's the only building block in a relational database. You only have tables, you don't have anything else, which is called join table or link table, or there are a number of other names for that table as well, which are usually just placeholder for representing many-to-many relationships, which have two foreign keys. Seldomly they have an identity, and sometimes they have some properties. But if you look at typical relational models, you have your entity tables, and then you have a gigantic number of join tables in between, because in real-world data, we actually have many more many-to-many relationships than other types of relationships. If relationships are optional, I can only represent that by putting a null value in a foreign key column. But having a null value in a column also automatically disables my ability to put a constraint on it. So as soon as I have optional relationships, I can't put foreign key constraints on them anymore. So that's why I lose then my integrity checks by the database. Something else that's really important in a relational database is that if you create or if you want to see your connections between two tables, you actually have to compute them at query time. So when I execute a SQL statement with a join operation, then at query time, the database has to go and find the matching primary keys for my foreign keys, or the other way around, using indexes or table scans. And the more data I have in my database and the more joins I have in my query, the more costly this gets in terms of both CPU as well as memory usage. And another thing that gets complex in a relational database, because it was not built for that, is representing data structures which are more complex than just simple tabular formats. For instance, if I want to represent lists or trees or similar structures, then I have to do a number of really weird things in the data model itself, and my queries get also much more complicated. especially if I have arbitrary depth and arbitrary length paths or trees. So if we summarize that, relational databases, despite the name, which is confusing, can't handle relationships that well. Because as soon as you start to add more relationships to your data model, you add complexity, implicit complexity, which is actually not part of the domain or business model, but is just a part of the database model. I also mentioned that performance degrades with the number and the levels of relationships, and so the query complexity grows. And something I haven't mentioned yet is the schema aspect. As you all know, relational databases are schema-based databases. That means you have to have, or you have to describe the structure of your database in terms of which tables do I have, which columns does each table have, which types do the columns have. And whenever I want to change something, I want to add new attributes, I want to add new relationships, I have to adapt the schema first, migrate the data, and which always causes friction between developers, DBAs, and people that deal with the database in general. And that's why it's not as easy as you want to build complex applications with a lot of connections in our relational databases. For building applications, we all also know the typical object relational impedance mismatch, where we have actually kind of in our applications a nice object model, which forms also an object graph. And as soon as you want to store, project it into our relational database, we are exposed to a number of pains that are not a lot of fun to deal with. So why is that so? Because actually the relational data model comes from a time when we used to deal mostly with form data. So kind of tabular forms, which are all very similar structured, contain the same data. It's really primitive, simple data. And actually forms, paper forms are not connected to each other, right? I mean, you might have like an employee number somewhere which appears in 3 places, but there are no real connections between forms. And that's why the whole data model was never built for that. And if you look at it, how, for instance, join syntax and foreign key constraints are represented in a relational model, it always feels like a bit like bolted on and not really integral part of the data model, actually well-designed part of the data model. I mentioned the other data volume aspect already, and also the representation of more complex structures, which are not so easy to store or to query. And for the performance aspect, many DBAs educate their developers then that even so your fine-grained normalized domain model might be nice for CRUD applications. As soon as you want to go into complex queries, you have to denormalize your data again to make it reasonably fast to query this data. Okay, if you want to represent heterogeneous or variable structured data in your relational database, meaning you have a lot of entities with a number of with a wide variety of attributes, like you have in today's web applications, where you have user-generated content that comes from other APIs, from other machines, from sensors, and so on. Then you have the problem that you get into really wide sparse tables. It's also in other systems like retail systems where you have like data interchange formats, which are really very, very variable. Then you have these wide tables with hundreds of columns, most of which are null in most cases. And then you just have a few columns that are actually set with values. And you have to store all this additional structural information, even though you don't have actually data in there. And of course, optional columns have also the problem that you can't put constraints on them anymore. As soon as you allow null values in columns, then a whole subset of the constraint enforcement of relational databases breaks down. I mean, you have to have it in the application level anyway, and so it's not so bad that you don't have it in the database, but many people really rely on the constraint checking of their database, and as soon as you go into the optional data aspects, then all of that breaks down, which is really sad. Okay, and the common structures Also interesting, especially if you come from object-oriented programming languages and if you want to represent, for instance, inheritance hierarchies in relational databases. That's also a lot of fun to do because there are different ways of doing that, but each of those ways are not really easy to do or manage to do it really well. But I won't go into these details. So if we compare those data models, let's start with the graph data model again. So what's really nice is that it's actually a very consistent data model. So across all the phases of your application development, you stay in the same model. So if you have a model on a whiteboard or on your paper app, you can just draw a data model. Everyone understands it. No one has a problem understanding these circles and lines or nodes and relationships, because in most cases this conceptual model is also example-based. So you have like Acme tag and Jupyter tag here, and your CEO and this and that person. So everyone can relate to this model. It's really easy to understand. That's the same for modeling conceptual models in other databases, right? Because it's on the conceptual level. But what gets really interesting is that in a graph database, you stay at the whole time at this same conceptual model. So you don't lose the nice structure, the high fidelity of this model, and all the information that you have in there from the beginning. You don't have to cut off anything there because your data model doesn't support it, but you can just keep it as it is. So if you look at the different phases, so in the business aspect of it, so you can discuss on the conceptual model with your business people, with your stakeholders. In the application, you have your object model, which is also a graph, which represents the conceptual model again. But as soon as you store this data in the graph database, it stays the same in the same shape. Right? So you don't lose any of this information or fidelity or richness anyhow. And it goes over all aspects of that. So in storage and processing and querying, even your queries look like graph patterns. And of course, as soon as you visualize your results of your query or your database in your graph viewer in your application again, you again have the conceptual model. So you can show your graph data in your graph database to a business person, and they can understand it, can reason about it, and even point out mistakes that you made when inserting the data, for instance, which is not as easy if you look at other data models. So here, for instance, I have an entity relationship diagram from WordPress, I think, which represents the aspects of the CMS system, and it's really hard to find what's actually the entities in here, what are just join tables in here, and so on. So I have some more examples like that very soon. So if you look at the relational model, there's a big discussion around normalization, right? So usually you start from the conceptual model with a model that's really well normalized. So you have your entities, attributes of the entities that are redundant are pulled out as separate entities, and it's really easy to reason about, really easy to understand, and that's where all the normal forms for relational databases come from. So you have your entities as tables, you have links for simple relationships, but then of course if you have the higher cardinalities, you have to add join tables, which kind of already pollute the nice model, but this kind of well-normalized relational model is well suited for CRUD applications, which always work with one entity at a time, or entities of one type at a time, and for OLTP, so online and interactive applications. But as soon as you want to query the data with more complex queries, then this fine-grained model breaks down because of the reasons that I mentioned before. And then you start to denormalize the nice model. You kind of merge tables, you duplicate data, you create really wide tables of denormalized data just to achieve the performance that you need to have a real-time or near real-time aspect there. But even so, in the past when I worked at, for instance, at retail systems, we had SQL queries with 35 joins in them, and if a user executed this query, it took like up to 10 minutes or so until the first results came back. And despite already lots of the database being denormalized. So even though it always goes only so far and you can't drive it to the end. If you compare the models kind of one by one, here we see our entities, in this case people on one side and the other, and the relationship in the middle, which is the join table in the relation model, and the relationship structure in the graph model on the right side. I have some more examples for comparing these models. So one is a simple organizational model. I have departments of an organization, which can have sub-departments again, and people working in those departments, and people also being participating in projects, and projects belonging to departments. Where we see in these colored boxes our entities, and all the non-colored tables are actually just join table. So for 4 entities, I already have to provide 3 join tables. And for more complex models, it's of course more. So how would that look like if I convert this from one model to the other? So I have my relational tables, my join table in the middle, and more or less it turns the join table into a relationship between nodes. And then we end up with a graph model which looks like this. We still have our entities, department, organization, person, and project. And all the join tables are gone and were replaced by relationships. So the model gets much easier to understand. A similar model, a bit more complex, is the Adventureworks model. And here I just circled the entities that we want to look at in red. And most of the other tables are actually just join tables that connect entities in a variety of ways with each other, or form categories, or trees, or relationships between our entities. So we have employees, products, suppliers, orders, and categories in here. So it's a retail application, of course. And if you look at the graph model for that, then it looks like this. This is about 13 tables, worth of 13 tables. So if you have 7 entities and 6 relationships, which are representing join tables, and this is already a quite large aspect of the previous model, just by removing all the intermediate crud. So, and Stefan did a really nice job of blogging about that. So if you get the slides, you can also look at the blog post, which details how he imported the Adventureworks model into Neo4j. When I want to move from my relational database to a graph model, I want to discuss 2 approaches today, which you can choose. So one approach is you first develop your graph model and then import into this model, which has many advantages and only a few disadvantages. So I call this model first. So you take your use cases, your user stories, your questions that you want to ask from your application, and develop your graph model from those. So you identify entities, you identify relationships from these, and build incrementally a graph model. With each new user story, a new aspect of the graph model is added, or an existing aspect of the graph model is enhanced and updated. And you kind of incrementally add more meat, more or less, to your graph model, and so you can kind of derive something that's really a minimal model for you to represent what the application actually needs in terms of structure, in terms of data, in terms of attributes, and so on. And then you take this nice graph model that you can also develop on a whiteboard without any computer support. Just grab a colleague, your use cases, and an hour or 2, and then you can develop your graph model. But then you take the data from your relation database and you import it into this model. So from the data that comes in, either directly out of the database, out of CSV files or JSON files or whatever, you actually create or update the graph structure. So you create nodes, you create relationships, you add information to nodes, you add information to relationships, you connect new data to existing data in the graph, and so on. So in many cases, that's a really interesting approach because it gives you the ability to have a really well-structured graph model, a graph model that adheres really closely or supports really closely your domain and use cases, and you just import the data that you need to support this model. And if you have a number of different applications and you want to keep them separate, either you want to build a microservice-based architecture or something else, then you can also have multiple of these graph models representing different aspects or different parts of your domain. Here. When would you do this? It's suitable if you do greenfield development. So you have something where you start from fresh with a graph model, and you have the ability to evolve this model and develop this model without being constrained by other things. Also, if you want to have an optimal graph model, so if you don't want to inherit all the craft that comes with the relational model, then you would take this approach. And then you only need a subset of the data. So you don't want to ingest the whole data from a relational database, but just a certain subset of that. Then you would also choose this approach. Also, when the relational model is already very, very denormalized, so when your model is not really able to support the kind of structure that you want to have, then you have to really take the data that comes out of the relational database and put it in the right places in your graph model. Or when the relational model that you already have is a bad fit for the use cases and questions you want to ask. So for me, this is the preferred approach. And I just want to show a simple and quick sample on how to do something like this. The full discussion of this approach is in the data modeling training and also in presentations from Ian Robinson. So here I would start with the user story. As an employee, I want to know who in the company has similar skills to me so that we can exchange knowledge. So we extract a question out of this user story. Which people who work for the same company as me have similar skills to me? So from there we can identify nouns and verbs like an object-oriented analysis, and from these nouns and verbs you can actually create graph patterns like this person works for this company or this person has a certain skill. And then we can convert these graph patterns into actual Cypher or ASCII art patterns. So person works for company and person has skill. And then we can generate sample data for this. There are certain tools out there like, for instance, GraphGen, which can automate large parts of that as well. And then from that sample data and from the question that we had with the graph patterns, we end up at the Cypher queries that represent our use cases. And if I do this for one story after the other, I enrich my graph model by one aspect after each other. And at the end, for instance, if I looked at all my 20 or 50 or how many user stories I have, I end up at a graph model which supports all these user stories, is minimal and is well suited for that. So that's one approach to incrementally develop a graph model. And then I would import into this model. So I would get the data and import into this graph model. And as I mentioned before, I will cover import, concrete import in the next webinar. To look into some guidelines for graph data modeling, one that I already brought up right now is really drive your graph model from your use cases and from your needs. Don't go from something that you make up or something that comes from another database or something that someone else tells you to pull in. Really look at what you want to do and what you need for that and drive your model from there. And rule number 2 is really, with the graph model, you have a really nice set of building blocks. You have nodes, you have labels, you have properties and relationships, and you can create really useful structures from that support your queries. Not just your entities and their relationships, but also additional structures that allow you to execute certain queries, for instance, in a better way. So one aspect is we should not store symmetric relationships twice. So if a person knows another person, that's an automatic bidirectional relationship. If I know you, you know me as well. And if I have a relationship like that, I only have to store one relationship and then rather choose to ignore the direction in the query, as you can see below. And I would only store bidirectional relationships if it's really semantically something different. For instance, if I want to store the follows relationship on Twitter, if I follow someone, it's not the same, or it doesn't imply that this person also follows me. So if I have really semantically different relationships, then I would store them independently. Another aspect as a modeling rule is how granular should my relationships be. So here you see on the left a very generic relationship structure, which is all relationships are just called connected to, which really doesn't give us any information or meaning. And on the right side, you see a too specific relationship structure, like Peter's work colleague or Peter's best friend. But what we actually want to have is really something that represents the relationships we have in our domain, the nouns, the verbs that are between entities, and which might be more or less specific. So there are some variations. For instance, I could say I have address relationships with a subtype property, or I could also say, okay, I have something like a work address and home address, because that's a really important aspect of my domain, and I oftentimes have to discern the two, so it's more efficient to represent the different types on the relationship name level. Another interesting aspect is how should I structure my data in terms of how do I store attributes? Should I put all attributes into just one node, like a gigantic document or like a JSON document? This makes sense for document databases. In a graph, I have the ability to actually pull out substructures into separate nodes to make the model nicer to work with and also more efficient. So on the right side, you see the kind of document-based variant, which is not what we want to do. And on the left side, you see the really fine-grained variant, where each attribute is actually pulled out into a separate node, which also doesn't make sense because all of these additional nodes don't have a conceptual and integrity in our domain. So there might be some attributes like an address, which I want to pull out. But the individual attributes, like, for instance, a name or a house number, if my domain is not really just managing map data for exactly these aspects, then those attributes don't have to be pulled out because they're not shared with other nodes, or they don't have an identity that makes sense to share them. So it's always a balance, of course, but we should aim for something that's more, it's closer to the object model, actually, where you have certain attributes that belong to your objects, and then you have semantic relationships to other entities which put your objects into context, or your nodes into context. Right, here's again the explanation for that. And that's something I mentioned also before, use the graph building blocks for structuring your data. So it's not just the domain entities that you have there, but you can also say, I want to structure something like an order in the graph between entities. And I can just create like a next relationship between entities. Imagine I have events that come in, and one event follows the other event, or I have a progression like a learning path of someone, or a website navigation path where someone moves from one website to the next. Of course, I could do something like storing timestamps and then ordering by timestamp or so, but it's much easier to navigate the graph structure if I create a relationship that orders nodes. Also, just to represent a join, we don't do something like I put a key in one node and I put a key in the other node, and then I do just in comparison where person dot I don't know, family name equals person2 dot family name, but I would create a relationship like married to or something like this. And also other things like trees, for instance, categories, product trees, organizational trees, or time trees, like in this example, or also a natural structure for relationships in the graph. So trees are actually a really nice model that I can easily represent in the graph. And there are a number of libraries which support that as well in Neo4j. Okay, that was the first approach. And the second approach, we actually reuse the relational model. Why would I use this? So when I actually have a well-normalized relational model, which I can use. Then I can extract the metadata from this relational model, meaning the tables, foreign keys, column names, and so on, and apply certain transformation rules that transform this relational model or entity relationship model into a graph model. And then with these transformation rules, I can read the data from the relation database or from another format and apply them while I'm inserting them into the graph. I can connect nodes via the original primary keys, so kind of recreate the join operation at insertion time. And then after I'm done, I can actually clean up the data by, for instance, removing these artificial primary keys that I don't need anymore because I have business keys that allow me to find my entities. When would I use this approach? When I have a large part of the relational data that I actually want to have in my graph, or I want to migrate from the relational database to a graph database. When my relational model is still really well normalized, so it was not denormalized for performance reasons. When I need a quick turnaround time, so I don't want to, or I don't have time to do graph modeling. So for instance, when I do spikes or proof of concept operations, or I just want to try something out really quickly to show that it's in principle. And then I have the ability to later migrate my graph or evolve my graph into a better structure or different structure, or clean out certain aspects of that later on. And how this works, just in a quick example. So here we have our well-known retail Northwind database. And this is the entity relationship diagram. So when I look at this, I start with what are my foreign keys? I find them and remove them, actually, because I don't need them anymore, because they become relationships to other entities. Sometimes I have to correct the direction, because in a relation database, if I have an n-to-1 relationship or one-to-n relationship, the foreign key is actually in the wrong table, so it points in the wrong direction. And then next, I can identify join tables. So join tables are tables with two foreign keys, no identity, and sometimes some properties which connect some entities. When I found the join tables, I can convert them into relationships as well. So like the simple relationship, the employee territories table becomes just a simple relationship there between employee and territory. And more complex join tables with attributes become a relationship with properties, like an order includes a product with unit price, quantity, and discount. And then we have a data model, which is more like a graph model, or looks like this. Okay. So if you look at modeling transformation, easy. Table name turns into the node label. Columns turn into properties. Of course, we can leave off properties or columns that are empty. We don't have to create properties that have no value. We could also leave off columns that just have the default value, because we can always infer the default value for non-existing properties. Sometimes we want or have to create values, convert values, either when Neo4j doesn't support the format, or if we want to have a different format in the graph for certain attributes. That kind of creates our nodes. Then, as next steps, we look at the foreign keys. And all the simple foreign keys, like one-to-one, one-to-many, and many-to-one relationships, turn into really normal relationships without any, or simple relationships without any properties. We can name into relationship type. We can also find better verb for the relationship types as well if you want to. And then lastly, we look at join tables. And join tables, as I mentioned, are tables without identity in many cases, and two foreign keys that don't have any additional or only a few additional properties. And those join tables are also turned into relationships in columns are turned into relationship properties. And then after that, we clean up the data model after we imported our data. So we remove technical IDs like auto-incrementing IDs. We keep domain IDs like ISBNs, for instance, or employee numbers or ASINs and so on. And then because these domain IDs and oftentimes are also unique, and for additional nodes by, for instance, the city field of an address or the name of a person or the name of a product or things like that. I can add indexes for those to have a quick lookup mechanism for those. And then we can adjust names for labels, relationship types, and property names to adhere more to Neo4j's style guide. One thing that could be a bit more complex is if my relational model has a lot of composite primary keys and foreign keys, then I have to find another way to deal with that. So for either I can temporarily to connect them, concatenate those composite keys, or I can create an array property that contains all these composite keys until Neo4j supports. In the next webinar, just a quick teaser, I'll show you how to automate this so that you don't have to do it manually. Okay, and closing, I also want to show you a fun project. David Poole did a really interesting thing, which was analyzing relational database metadata in Neo4j. So what is this kind of metadata? It's catalogs, schemas, views, tables, foreign keys, columns, stored procedures, indexes, constraints, and so on. This is the metadata, and questions that I could ask, and many more, of course, are which tables are connected and how, which columns actually have no constraints, which views are no longer used, or which tables and columns are used by the stored procedure, and so on. Or how higher level structure and relational model. And what he did was he first defined a graph model for the relational metadata, more or less what I just spoke about. And then he created the system tables of SQL Server. If you use Java, you can also use JDBC's database metadata for that. And then he generated Cypher statements to create data in a graph that represents this metadata. He created a graph and then he queried it. And if you look at the query model, some examples here, he created actually views and stored procedures to represent Cypher statements for tables and pictures for these. All together, so fuse the nodes and relationships and just put them into a single Cypher script and import it into Neo4j. And this is the Adventureworks metadata as a graph. So you see the different types of tables like production table, sales table, person table as labels with the different names. And then he, for instance, did a shortest path search between product photo table and customer table. And you see all the tables that are in between this product photo table and the customer table. So of course it's from photo to product to offer to order to customer. And that's something you can use to really find, it's like software analytics for relational databases. Kind of a fun project. So there are many meetups worldwide. We have a lot of books. We have online training. We have training classes online and offline, our Google group on Stack Overflow, and so on. So there are many, many ways. And I also added some resources here, especially the developer section of the website, Neo4j GraphGIS, which are really rich in example data models for graphs, Ian Robinson's presentations on graph data modeling, and of course our training classes, our office hours, and the free books that you can download as PDFs, like Graph Databases book, which is now available as second edition, and Learning Neo4j. Okay, and that's it. And I'm looking